Good afternoon, everyone. I'm going to be talking about how one tunes an underwater communication link. The idea is that we optimize a point-to-point communication link to maximize the data rate performance. So it's a signal processing setting, but we use techniques from statistics and machine learning to do the optimization. So let's start. The underwater channel is diverse. Communication performance depends on a lot of physical environmental factors, including geometry of the link and the underwater bathymetry and geography, as well as details of the physical layer implementation on your particular modem. So if any of these change, the communication performance is going to change also. And today we have quite a diverse array of physical layer implementations. So for example, the WUI micromodem is based on a frequency hopping BFSK/PSK scheme. We have other modems like the UCSD modem, which is based on a spread spectrum implementation. There's the Evologics modem, which has a sweep carrier based physical layer implementation. And of course, there's also the UNIT2 modem, which is a modem used in ARL. And that's based on an OFDM with a BPSK/QPSK implementation. So we have you could implement your modem in using any of the popular physical layer modulation methods. And the other trend we see today is that a lot of modems are increasingly software defined. By that I mean you can set a lot of parameters on the modem through software. So just to give you an example, the UNIT2 modem can actually switch between coherent or incoherent communication. You can use either a time or frequency differential mode, and you could switch between BPSK or QPSK. There are a number of things you can set on this modem. So for example, you could set the number of prefix and suffix, the prefix and suffix lengths, which can go from 0 to 1024. You can choose the number of carriers, the number of null carriers, the kind of error correction code you want. So all of these things can be set in software. So given that we have a wide array of underwater channels to operate in, and that we have a variety of modems whose parameters we can set, this leads us to the question that is it possible to derive a learning algorithm that can maximize the data rate performance of a point-to-point communication link? And we want this algorithm to work for all communication channels and on all modem implementations. So we seek such an algorithm in this work. So to be more detailed, this is the problem setting. What we need to develop is a link tuner, and the input to this tuner is essentially a packet stream. And there are two kinds of packets that stream in. There are data packets and there are test packets. And the output from the tuner is a series of scheme recommendations. A scheme is basically a set of values for all the parameters in your modem. We have feedback for all our, the modem has feedback for each of the packets that it sends out. So if you send out a data packet, which basically carries user data information, then the feedback is in the form of whether the packet was successful or not, or was it a failure. You can also send out test packets which don't carry any user data information, but they can tell you what was the bit error rate on that packet. So given this information, can you give out scheme recommendations whenever requested by the user? So before I describe the link tuner in full detail, I will go through a few of the design choices that we made while developing the tuner. So the first thing to consider was an online tuning mechanism versus an offline tuning mechanism, and we chose an online tuning mechanism. The reason for this is essentially because of temporal variations in a given point-to-point link. So the same point-to-point link in the same location is going to perform differently is going to perform differently at different points in time, and therefore you want a tuner that will continuously respond to changes in the channel and tune the link accordingly, and hence you need an online tuning mechanism. The process of link tuning can also be, you can think of it as a sequential decision optimization process, where you essentially make a series of decisions and you want to optimize the whole series. So basically there's a transmitter and a receiver, and the receiver sends a transmission, and the transmitter sends us a packet with certain parameters encoded in a certain scheme, and you get feedback about it. And then you need to make a decision about what scheme should I use next for my next transmission. So you make these decisions periodically, and for a link tuner, what you want to do is you want to optimize the entire series of decisions, and hence we choose an online tuning mechanism. The other two important design choices that we made are to base the tuner is to use a data-driven tuner as opposed to using a physics-driven tuner. What I mean by that is that the input information to the tuner is just BER information. So just bit error rate information drives all tuning decisions. This has the advantage of, if you do this, you have the advantage of being able to use this tuner on any modem implementation, because I guess you can safely assume that no matter what kind of modem implementation you have, you will always have BER information. So you don't really need any custom signal processing to drive the tuner. And the other thing to keep in mind is that we are optimizing for average data rate, and we are not really searching for the maximum possible data rate that you could attain. The reason we do that is because as a user, you just care about how fast can you transfer a given file. And you don't want to be spending too much time in the tuning process if you just have a little bit of data to transfer. So when we calculate the average data rate, we include the time taken for tuning in that computation, and that's what we try to optimize for. An important theme, recurring theme actually in this work is the exploration versus exploitation dilemma. And it goes like this. At every tuning, at every decision epoch, you have basically two choices. You could either explore or you could exploit. So exploration consists of trying a new scheme, and if you do that, you can make better choices in the future. Or you could just use the best known scheme today, and you could increase data rate right now. So any tuner that uses a purely exploration or an exploitation-based strategy is going to perform poorly, and balancing both of these aspects is essential to achieve a performant tuner. So that leads us to a very famous problem in the statistics community called the multi-armed bandit problem. The multi-armed bandit problem was people came out with that in order to model the exploration versus exploitation dilemma in a more formal manner. So the multi-armed bandit problem goes like this. Imagine that you're a bandit and that you have some number of coins in your pocket, and that you can play a series of slot machines. Each of these slot machines, when played, will generate a reward according to an unknown probability distribution. And the more often you play a machine, the more you learn about the underlying probability distribution. And the multi-armed bandit problem is the following. Given a finite amount of coins, in what order must you play the arms in order to maximize the total expected future reward? So we use, so the analogy to the link tuning case is that each of these slot machines essentially corresponds to a scheme. A scheme is a set of parameter values that you set on your modem. So if you solve the multi-armed bandit problem, you could, that is essentially very similar to solving the link tuning problem. So this is the overall architecture of the link tuner. It basically has three essential components. There is a scheme selector, which is basically a solution to the multi-armed bandit problem. But there are two other components. We have them because we can't use the multi-armed bandit setting directly. So there's a BER estimator, and there's also a scheme generator. So I will go through each of these components in a little bit more detail, and that will illustrate better how the architecture works as a whole. So one of the things that